So today we're going to be talking about the identity matrix. Now, the identity matrix comes around because in standard algebra, when you multiply a number by 1, nothing happens. There's no observable result. So this is what we call the identity property of multiplication, meaning what can you multiply by where there's no observable effect. The same goes with the matrix. If I can multiply by some sort of matrix to get no observable effect, what would that matrix be? Let's take a look at what's going on inside of this question right here. If we have a matrix 1, 5, negative 4, 2, 0, negative 6, we want to know what matrix could we multiply it by. And let's do this matrix in, let's say, in red, so that our answer is spit out as a 1, 5, negative 4, 2, 0, negative 6. And so let's take a look at what's going on with this. And so now most commonly, students like to answer something like, let's go with 1. And yes, albeit if we had a scale factor of 1, we'd be able to translate that in. But we're looking for something that is in terms of the original question. So if I'm having a matrix, what matrix could I multiply by? Not a scale value. So albeit 1 is usually a good first answer, let's try something else. And so a second common answer is, well, how about we just multiply it by a series of 1s? Let's say 1, 1, 1, 1, 1, 1. But the problem with multiplying it like this is when we go to find the dot product, we've copied over the matrix. We notice that my row and my column doesn't have the appropriate amount of space. The 1 times the 1 and the 5 times the 1, but then I have this extra piece that doesn't match up anywhere. And we're like, okay, it can't be the same shape. It must have some other shape. And you might be even more intuitive to say, well, if there are 2 rows right here and I have 2, how about I just go ahead and make it a 2 by 2? So as of right now, we're dealing with, I have a value of 1, 1, 1, 1. And that makes sense because this can be found with the dot product. The problem with this is when I find the dot product of my first one, I have a 1 by 1 plus a 5 times 1. So I'll end up with a 1 plus 5, which is a 6, which is not what I want in my first column. I just want the number 1. So you might ask yourself, well, okay, if I want the number 1, I don't want the number 5, how about I make that a 0? So if I turn that into a 0, okay, now the 5 goes away, I'm left with a 1 in the top left corner. And let's make sure that works on every piece. So that'd be negative 4 times 1, and the 2 disappears, so the negative 4 stays. 0 times 1, the negative 6 disappears, but we wanted a 0. And so I'm going to look over here, and I'm like, okay, cool. So if I go back and I redistribute this row to my second column, as of right now, I have a problem. I have a 1 times 1 plus a 5 times 1. And I only want the value of 5 to stay. I want the first value of 1 to disappear. So the way that I make that is I make that a 0. And I can check to make sure that works all the way down, and it does. Because what I'm looking at is the 5 stays, the first one disappears, the 2 stays, first one disappears, the negative 6 stays. Boom, so we have ourselves the identity matrix. And now that was a long walk for a short drink of water. So there's got to be an easier way to do this. And there is. So now that we've seen how this works, let's go ahead and get rid of this right here. And let's look at the dimensions of the matrix. Horrible erasing job, but oh well. So the dimensions of this matrix are a 3 by 2. And we could look in order. Our first mistake was saying, well, we made the wrong set of dimensions. In order for this matrix to be compatible, we know that those inside numbers must match. So what I'm looking at is I have to match this 2 with this 2. If they don't match, I can't multiply them. So it has to be a 2. The second thing is I want my matrix to be a 3 by 2. So whatever I'm going to multiply by, I want this to produce a 3 by 2 matrix. Well, I have my 3, which means that has to be a 2. So I know that my matrix must be a 2 by 2, where I only keep the first thing, only keep the second thing, and so on and so forth. So no matter what's going on, I'm going to take that second number in the matrix, the number of columns I have, and duplicate it twice, and that will be my identity matrix. We've got 3 different guides about examples of how to do that. This is a 3 by 2, which means my identity matrix is a 2 by 2. This is a 2 by 3, which means my identity matrix will be a 3 by 3. This is a 1 by 4. My identity matrix would be a 4 by 4. I literally just keep the second aspect of the matrix, the second element, which is going to be the number of columns. 1, 2, 3, 4 columns, it's a 4 by 4. 1, 2, 3 columns, it's a 3 by 3. 2 columns, it's a 2 by 2. I don't care how many rows it has, I just care how many columns. So we're going to take a look at a few of these problems and create the identity matrices that we would have. So let's go ahead and set up. The dimensions of this matrix are 1 row, 2 columns. I know that in order for my matrix to be able to be multiplied, I'm going to have a 2 by something. 2 by what, you ask? Well, the identity matrix must have the same dimensions, which means I'm going to repeat that a second time, a 2 by 2. Well, what is that 2 by 2? Well, I know that if it is a 2 by 2, I keep my first and get rid of the second. And then I'm going to keep my second and get rid of the first. That's the matrix. If I were to find the dot product between these two things, I will get an answer of 2, 3. Just box that up, just because, boom, it looks nice. And so if I move to the next one, I'm going to do the same process. This is a 2 by 2 matrix. I want to find out what can I multiply by to get that same answer in response. And I know that these must match in order to do the dot product, so I'm going to say 2 by something. The next thing is if I want a 2 by 2, I know my second number has to be a 2 as well, which means, again, I'm dealing with another 2 by 2. So I'm going to multiply that matrix times a 2 by 2 matrix where I keep the first thing, get rid of the second, and keep the second and get rid of the first. If I find the dot product between those, what you'll find out is that you will get a 9, negative 4, 3, negative 12. Boom, as your answer. And then if I have something like number 7, this won't produce a 2 by 2 matrix. This is a 3 by 3, in which case, again, the same set of rules apply. In order to multiply this, it has to be a 3 by something. And if I want the same dimensions, I'll just say, okay, let's take the number of columns and make it the number of columns over here, and boom, I'll produce the same dimensions. So it'll be a 3 by 3. In this case, I keep the first number, get rid of them. I keep the second number and get rid of the other 2. And the last one, I only keep the third. If you check the dot product for that, you will get the same matrix in response. Boom. There we go. So we see it was a little bit of an intellectual leap as to what's going on with the identity matrix, how is it constructed, but once we know how it's constructed, it's a pretty straightforward process. So that is going to bring us to the end of the front, and let's take a look at the back. So with this, what we're going to be doing is this is the last step before we start using these matrices to apply to scenarios. We want to use a form of Gaussian elimination to produce reduced row echelon form. What reduced row echelon form is an identity matrix. So let's go ahead and get that set up and say, how do we approach that? Well, with a 2 by 2 matrix, it's going to be 4 steps. We're going to attack the matrix in a counterclockwise direction. We're going to reduce this to the 1, turn that into a 0, reduce this to a 1, and then turn that into a 0. And just follow our way around the clock. So let's take a look at the first one. our first step is to ensure the lead pivot is 1. So what we're going to do is we're going to say, hey, I want to make sure my lead pivot, which is the top left corner, is going to be a 1. I don't care what else is going on in the matrix. I want that number to be a 1. Look over here. What do I multiply or divide by to get that into a 1? Well, nothing. I don't need to do anything for this one, which means the rest of them, 5, 3, and 10, are good to go. My next number, I'm going to move down to the 5. So I want to cancel out the non-pivot below. So what I want is I want this space right here to be a 0. I have my 1 up here. I don't want to change that. I want to turn that 5 into a 0. So what row operations do I need to do to cancel out that 5? Well, what I would do is I'd say, okay, first off, I need to write a rule for row 2. I'm going to take row 2, which is currently 5, and I'm going to subtract 1 from it 5 times. So minus 5 of row 1. That's going to allow that 5 to fully cancel out. Now, the problem is that it's going to affect the entire row. So I'm going to have to look at these and say, okay, cool. Well, the first row didn't change, but I do have 10 minus 5 threes. 5 threes is 15, so 10 minus 15 is negative 5. So I canceled out the non-pivot. The next thing that I'm going to do, I'm slowly working my way around the matrix. I want to keep my 1, I want to keep my 0, but my next thing that I'm paying attention to is going to be that number right there. I want to ensure that new number is 1. Okay. So what do I multiply a negative 5 by to get a 1? Well, again, I'm making a rule for row 2. So to get negative 5 to be a 1, I'm going to divide it by itself, which means I'm going to multiply by 1 over negative 5. Multiply by the reciprocal. And the good part about this is it doesn't undo our work in the previous step. If I take 0 and multiply it by negative 1/5, I still have 0. It doesn't undo the hard work that we did. And then the last step is I'm going to slowly work my way, boom, 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 around the matrix. I want to make sure that this number right here is my final 0. So I should hope that none of these change. So how do I get the 3 to become a 0, not affecting any other value? Well, I'm first off going to make a rule for row 1. And I'm going to say, well, if my row 1 is a 3, I need to take away 3 of row 2. So 3 minus 3 would give me a 0. And the good part is it won't affect my first term over here, the element in my first column, because 1 minus 3 zeros is going to stay a 1. Boom. And we have completely reduced this into reduced row echelon form. And let's go ahead and take a peek at the next one. The next one, we're starting with this matrix. Now, you might ask yourself, what order does it really matter in? Well, the order, if we look at this, we could do them out of order. And let's, for a second, assume that we're not going to go in that clockwise direction. And let's take this as 1, negative 4, negative 2, and 5. And what we're going to do for just a moment is we're going to say, hey, let's go ahead and reduce the 5. Let's change our direction of attention and start right here. Okay, well, that would mean that I'm going to say row 2 is going to be replaced with 1/5 of row 2, which is going to make that 1, negative 4. That does give me a 1, which makes me happy, but this is going to be negative 2/5. And then if I wanted to go ahead and cancel out that negative 2/5, what I know is that if my attention is on this, and I say, okay, how many 1s will it take to cancel out the 2/5? Well, it will take 2/5 of row 1. And luckily enough, that will mean that that is 1, negative 4. I have now canceled out that successfully, but I will have to add 2/5 of 4 to 1, which means 1 plus 2/5 of negative 4. That's going to be 1 plus negative 8/5, which is going to be 5/5 minus 8/5, which is negative 3/5. And what I just did right here was I undid what I did in the first step. Now, albeit I am slowly getting this matrix simplified, I undid my work, which in this case didn't affect me, but it slowed me down by 1 step. But if I had completely eliminated out the entire row, let's say in doing that process, I zeroed out everything and I had no row 2 anymore. That presents a problem. So the manner of which we solve any one of these is, let's write a rather large matrix and see how we do it. So 1, 2, 3, 4. Okay, so I'll have this matrix. Now, what we'll do is that these are going to be our pivots. I will eventually want these to be 1s, and I want everything else to be a 0. The order of which we're going to attack these in is we're going to start in row 1 and move our way down the rows. And what we're going to do is we're going to zero out everything leading up to the pivot until we hit it. So I'm going to reduce the pivot, zero out everything along my way until I get to the pivot and reduce it. So 0 out the 9, 0 out the 10, reduce the 11. Then I'll come down, 0 out the 13, 0 out the 14, 0 out the 15, and reduce the 16. So I'll go 1, 2, 3, 4. Once I get to the bottom, I'm going to work my way back up and say 0 everything out. All the way over. I don't need to get back to the pivot because the pivot should stay a 1. So 5, 6, and 7. And that's going to be the order that we do things in. It's still in a clockwise direction, but it's always leading into and through the pivot. So understanding that, why don't you go ahead and try out number 12. Unpause the video when you're done and see how well you did. Okay. So what we know on number 12, let's zoom out real quick, is that I know out of my 4 steps, go ahead and write my outer matrices. What I'm looking at is I'm going to slowly work and I'm going to say, make sure this is a 1, 0, 1, 0. Here's where my attention is going to be. Top left, move down, move over, move up. So let's move through those steps. As of right now, to get from a 1 to a 1, nothing changes. My steps are good at this point. To get from a -2 to a 0, well, that's going to take 2 of the things above it. So row 2 is row 2 plus 2 of row 1, which means that -2 plus 2. 2 of the things above it is -8, so 5 minus 8 is -3. And because I did not affect row 1, boom. The next thing is I want this -3 to turn into a 1, which means I will need to write down a rule for row 2 and say, okay, I'm going to multiply by the reciprocal, -1/3 of row 2. I'm going to work that all the way across. -1/3 of 0 is 0, and row 1 remains unaffected. The last thing I'm going to do is I'm going to ensure that -4 becomes a 0. So I need to make a rule for row 1. And that's going to take exactly 4 of row 2. So row 1 plus 4 of row 2. So -4 plus 4 is 0. 1 plus 4 zeros is 0, so 1 plus 0 is 1. And then row 2 remains unaffected. We created our identity matrix, or what we call reduced row echelon form. And there we go.